Did you hear that message? Call recording is on?
Yeah.
Okay, good.
I'll be right back. Hold on.
All right, go ahead. MPLS switches.
All right, I'm ready.
All right, very good. So we had just started this conversation about multiple access links and protocols. And
I'm hearing some static.
Okay. I'm using my standard microphone. All right. Is that any clearer, Sam?
That's clearer.
Okay. I put my mic a little closer to my mouth. All right. So we were saying that we were evaluating or just starting to get into this multiple access links and protocols. And we had said that there are two types of links, a point-to-point link, okay, or PPP for dial-up is one example, or point-to-point link between an Ethernet switch and an Ethernet host. Another type is broadcast, where we use a shared wire or medium. And with respect to shared wire, the old-fashioned Ethernet was considered to be a broadcast type link. Also upstream HFC and the 802.11 wireless. So any kind of wireless configuration was considered to be a shared medium. In other words, we're sharing the airwaves. Okay, so in either case, we've got a single shared broadcast channel, two or more simultaneous transmissions by nodes creates interference, and we often describe this interference as a collision, in which if a node receives two or more signals at the same time, it is identified as a collision, which then forces the transmitting nodes to have to retransmit. Multiple access protocol is a distributed algorithm that determines how those nodes share the channel, okay? and determine when a node is allowed to transmit. And there are a couple of different models here that we use. Communication about the channel sharing must be done in the channel itself. No out of band is allowed to be used. In other words, the actual channel that we're using to transmit data must also provide or allow for communication with regard to the status of the channel and whether or not there are any collisions and so on.
Okay.
Broadcast channel of rate R bits per second. When one node wants to transmit, it can send at that R rate. When M nodes want to transmit, each can send at an average of R divided by M. So if R is 100 bits, or let's say 1,000 bits per second, and you've got 5 nodes on your network, so M is 5, then 1,000 divided by 5 is going to be 200 bits per second. That's on average. Many times this type of configuration is fully decentralized. In other words, there is no central point that controls the access to the medium. So no special node to coordinate transmissions, and there's no synchronization of any clocks or slots. It's very simple and very straightforward.
Yeah, could you slow down a little bit with this?
Sure. Okay. When we talk about broadcast type protocols, all right, we often group them into classes. And those 3 classes are channel partitioning, random access, and taking turns. And let's go through each one. Channel partitioning, what that does is it breaks down the full bandwidth of the medium, and it breaks it into individual channels such that each channel is carrying a different stream of data. And we'll see this in a moment. There are some additional slides that will allow us to demonstrate this in greater detail. So
Okay,
we want to
go over similar scenario problems with that.
Okay. Yeah, you just came back to me and you were breaking up seriously. So that was kind of interesting.
It's because it was because of the thunderstorm.
It may be.
Yeah.
You know, there may be some service issues.
Yeah.
So I'm sorry, you broke up so badly I couldn't understand what you were saying. Go ahead.
Could we do like some similar problems related to these scenarios?
You're going to see that. There are slides, Sam, that show us this, okay? So,
okay.
Yeah, just give me a moment. Let me go over the 3 types, and then we'll get into each one, all right?
Okay.
Random access, the channel is not divided, but it's allowed to have collisions. This is the typical old-style Ethernet is random access, okay?
Okay.
Channel partitioning is something that we often do with, did you ever have DSL in your home?
Once. It was back in 1998.
Right. Now, DSL uses partition channeling, or channel partitioning. And we'll talk about how that works, okay?
Okay.
Then we've got something called taking turns. And this was probably something that your father was probably more knowledgeable than I, because IBM was famous for using taking turns. Specifically, this is where IBM's token ring got its name, is that it used tokens in order to allow for taking turns from different nodes. But again, we've got some examples, and we'll get into those momentarily. So here we are, channel partitioning. This is the first type that we had talked about. And within channel partitioning, there are a couple of different examples. There is what we call TDMA, or time division multiple access, or FDMA, which is frequency division multiple access, okay?
Right.
In both cases, what would happen in a given time segment, we would generally divide that up like with a T1. Have you ever heard of a T1?
No.
T1 is an older WAN technology that we used to use. And what was great about the T1, it was provided by the Bell Atlantics, or the Bell telephone system, and Verizon. And the great thing about the T1 was that it was a service that could be provided over a very long distance. Okay.
Right.
As a result, it was available almost everywhere. You could get a T1 anywhere you wanted. The problem is that T1s were typically very expensive. So before I even got my high-speed internet, through Comcast or Verizon, I had a T1. And that T1 would run at 1.544 megabits per second. Okay? So 1.5 bits per second. Extremely slow in comparison to what we have today. But guess how much I paid for that service? Guess how much a month I paid for that service? Any guess, Sam?
I think it was very expensive.
I'll take a guess.
It was like $200 a month.
Okay, it was $725 a month. So it was very expensive. And back then, 1.5 of bandwidth was doing pretty good. In either case, what happens is we take that bandwidth and we break it into time segments. And then within that time segment, we also break it into what are called slots. And each slot is carrying a different data stream. So in our example here, you'll notice that we've got 6 workstations. So we've got 6 stations, and we've got 6 slots inside our frame. And if station 1 has anything to say, it's going to put it into its slot. And if station 3 has something to say, into station 3. But you'll notice that there's nothing in slot 2 because system 2 is not transmitting. Okay?
Right.
So slots 2, 5, and 6 are idle. And that was one of the problems with time division multiplexing, is that you had these idle slots. So, your bandwidth was literally going to waste. But it was, however, a very effective way of handling it. And because the need for bandwidth way back when was considerably lower than what it is today, okay, it was not a problem back then. In fact, in a T1, I told you how slow a T1 could run. T1s were often used for handling multiple telephone connections at the same time. Guess how many connections, telephone connections, one T1 could handle? Take a guess.
The T1 could handle,
at 1.54 megabits per second, how many telephone conversations do you think you could be having at the same time on a T1?
I think you can have about 2 to 3 telephone conversations at the same time.
Okay, well, that's a good guess. But the actual answer is we could have 24 telephone conversations at one time. Okay? Now, what I used to do way back when was I would take a T1, and as I told you, it would cost me about $725 a month. And what I would do is I would split the bandwidth of the T1 in half. And I would allow for half of it to be used to support 12 telephone lines at one time. And the other half, which was approximately 750 megabits, or I'm sorry, 750 kilobits per second, okay? I would split it between telephone and data. So for a small office, and many small offices didn't have more than 12 telephone lines often, okay? For a small office, the T1 was perfect. And with 750 kilobits per second, okay, what would end up happening is that was generally a good data bandwidth, okay, to use for most internet access. And this was back in the early 90s, okay? All right, so that's TDMA, and a T1 is a very good example of TDMA. All right, another...
What could he ask about this? How could he ask it?
Okay, he's going to ask that TDMA stands for Time Division Multi-Access. He's going to ask how is the TDMA divided up, and you're going to say that it's divided into time slots. Okay?
It's divided into time slots.
Yes. And one of the problems that you have with TDMA is unused slots go idle.
Yeah, but he said for the exam it's gonna be like all multiple choice, except
Right.
except one question.
I don't
for the final,
understand. Except
yeah.
one question. All your questions are multiple choice except for one question on the final. Okay. So he's probably going to give you maybe an essay for that one question.
I think he was going to go to the 57 protocol stack.
All right. That's why it's important to really go through these PowerPoints and understand what they're doing here, because this is great stuff to where he's going to take test questions out of. All right, next.
And can we go through a similar example with that?
What do you mean a similar example?
Like a similar, for example, TDMA.
No, there is no similar example. This is it. Okay? That the channel is divided into time slots. Every frame has the same number of time slots, and each slot, okay, is assigned to a given station.
So that's it.
Right.
Just one.
Yeah, there's no example here. See, he says it right here. Each station gets a fixed length slot, and when we talk about slot, we're really talking about time. So the length of the packet, or the length of the slot, is equal to the packet transmission time. Okay?
Right.
So he's telling you everything right there.
Okay.
Okay? Okay, now, frequency division multi-access is what is used in the old style cable television. In old cable TV, what they used to do was they used to take the frequency and divide it up. You know how, are you familiar with FM radio?
FM?
Yes. You've heard of FM radio, right?
I heard of it, but...
On your car. In your car. Don't you do you listen to the radio in the car, or do you have satellite radio?
I listen to the radio in the car.
What channel do you listen to?
98.1.
Okay, so 98.1. What is 98.1? What does that represent, other than the name of the radio station?
That represents That represents the channel that you're doing for FDMA.
That
Like the
represents
frequency.
that represents the frequency. So what happens with FM radio, they break up the air waves, okay, into frequency channels. So that radio is a wireless communication medium, correct?
Correct.
Okay. This, however, is not wireless, it's wired. We're often talking about wired. And in this particular case, we are also breaking up the channel by frequencies, and each channel gets a frequency ID, just like 98.1, but it's typically a higher value. Don't worry about what the values are, okay? So in this case, each station is assigned a fixed frequency band. Like one station is assigned to 98.1. Another station band is assigned to, 101.5. Okay? You don't want the frequency bands too close to one another. Otherwise, they run into one another. Okay? That's why you generally will not see, in the Philadelphia area, you won't see a 98.2. Okay?
Okay.
You said you listen to 98.1, right?
Yes.
Okay. So you're not going to see a 98.2 in the Philadelphia area, because if we did, that channel would be so close to 98.1 that you would literally probably be able to hear 98.2 on the 98.1 channel. Does that mean that nowhere are you going to find a 98.2 channel?
No.
What happens is maybe if you go out to, let's say, Pittsburgh. If you were in Pittsburgh, do you think you would be able to get 98.1 on your radio?
You could be able to have like a 98.1 video?
Or you're going up to Kingston tomorrow, Kingston, New York, right?
Right.
So that's like 4 hours away. Do you think you'll be able to listen to 98.1 when you get up there?
I think it could change depending on where you are.
Well, wait a minute. If you dial when you're in Kingston, New York, seeing your relatives, and you dial to 98.1, do you think you're going to hear 98.1? Yes or no?
Yes.
No. When you get to Kingston tomorrow, I want you to tune your radio to 98.1, and I'm going to tell you what you're going to hear. You're going to hear static. Okay?
Right.
In fact, I'll bet that you can't even hear 98.1 any further north of Flemington, New Jersey. Do you know which way you're taking to go up to New York?
Like Flemington, I don't know. It's like Flemington, New Jersey.
Okay, well, I'll tell you what. When we get in the car, when you and your mom get in the car and we start studying together, we'll ask your mom which way we're going to get up to Kingston. And I'll tell you when we're going to lose 98.1. But the point that I'm making is 98.1, because it's a radio station, only goes geographically just so many miles. It can't go any further than 20 miles maybe, okay? So I could probably have another station, okay, such as 98.1 up in New York without a problem. Because I know the New York 98.1 is not going to interfere with the Philadelphia 98.1. That's why many times when they call out their channel number, they'll also have call letters as well, and they may even mention the city, so you know where that's coming from. in either case, getting back to this, just like the radio is broken into frequency bands, we can also break the frequency of a cable or a cable into frequency bands as well. And traditionally in the past, that's what Comcast used to do to get all of its TV shows coming through. That's how it was able to show you like HBO and Stars Network and ESPN, all of those different channels. Okay? Because they use a frequency bands. Okay? And
So,
go ahead.
So, for example, it could be Verizon Wireless?
Verizon Wireless does not use frequency bands, okay? Well, no, I take that back. I'm not exactly sure how Verizon Wireless handles that, whether it's FDMA or TDM. Yeah, FDMA or TDMA. I don't know which one they use.
Could he go into examples on the tabs, or would he just go basically with the...
He's going to go with what you're seeing right here, Sam. Okay? He's
Okay.
not bringing it up, so... You know, whatever he has here or he's mentioning in the book, and that's why it's so important that we read that book. But here, what he's doing with the PowerPoint is he's summarizing the most important points from the book. Okay. So, you know, my recommendation to you is when you are not working with me, that you are going through some of these old PowerPoints and you are reviewing this material, as well as, and if you're not sure about what he's saying, take a peek in your book at the chapter to get a better explanation as to what he's saying here.
Right.
Okay.
I'm trying to do that, and I'll try and do that. And I've been studying the PowerPoint. I've been also studying the definition in terms of the book too.
Good.
But I might need some examples.
Well, that's fine. So when you have difficulty understanding a particular section, write that section down so that when you and I get together, we can go over it. Okay?
Right.
All right, very good. Cool. So now we're talking about random access protocols. And in this particular case, when a node has a packet that it wishes to send, okay, it essentially transmits at the full channel data rate of R, okay? There's no a priority or prioritization coordination among the nodes, okay? Two or more transmitting nodes, if two stations attempt to transmit at the same time, we have what's called a collision, and collisions should be avoided. So, random access MAC protocol specifies, 1, how to detect when a collision occurs, and 2, how to recover once the collision has been detected. Some examples of random access MAC protocols, and MAC means Media Access Control, okay?
Right. Media Access Control Protocol.
Correct. So some examples are slotted Aloha, Aloha, CSMA, CSMA-CD, and CSMA-CA. And we're going to go through each one of these, okay? We're going to talk about each one of these examples, okay?
Okay. Is there a similar pattern with these or no?
Now you're going to see, we're going to talk about Aloha to begin with, slotted Aloha, okay?
Okay.
All right. So, slotted Aloha says that all frames will be the same size, okay? Time is going to be divided into equal slots, size slots, okay? Big enough to fit a given frame, okay? So 1 frame in 1 slot. Nodes start to transmit only slot in the slot beginning, okay? They
Right.
can't transmit at the middle of the slot. They have to time it for the beginning of the slot. All right?
Right.
I'm trying to think of an analogy or an example that you can use here. Yeah, really don't have anything. Well, they've got some diagrams after this right here, okay? So we'll look at
Right.
that in just a moment. All right, so anyway, nodes are synchronized. In other words, all the nodes know the beginning of each slot so that when they are given access to a slot, they can start filling that slot with the frame that they have to transmit. If two or more nodes, however, transmit in a slot, all the nodes then detect the collision. And then there's going to be some kind of recourse in the event that the collision happens. And we're going to talk about that over here. So when a node obtains a fresh frame, it transmits, okay, in the next available slot. If it detects no collision, then the node can send a new frame in the next slot. However, if there is a collision, the node has to retransmit the frame in each subsequent slot with the probability of P until success. So let's take a look at the diagram here. So here are three nodes, okay? Three nodes that are attempting to transmit. You can see node 1 transmitting, and each one of these is a slot, okay?
Right.
So what's happening is node 1 attempts to transmit into this slot, okay? And then it probably collides and it attempts to transmit again in slot number, in the third slot here. That collides. System number 2, or node number 2, finally gets in the next slot. And you can see each one finally finishes communicating over here because it finally gets an open slot. And then node 3 finally finishes here. So let's look at some of the advantages to a slotted aloha. First, there's a single active node can continuously transmit at the full rate of the channel. So if there are no other systems that are transmitting, a given node can transmit at the full transmission rate. This particular protocol, slotted aloha, is highly decentralized, okay? Only slots in nodes need to be in sync, okay? It's a very simple protocol, all right?
Okay.
Some of the disadvantages to slotted aloha is that there are quite a few collisions, and we have what are called wasted slots. We also have idle slots in which nothing is being transmitted. Therefore, bandwidth is being wasted. Nodes also may be able to detect the collision in less than time to transmit the packet. Okay?
Right.
So they may not always have enough time to detect that collision. And there has to be synchronization of the clocks between the nodes. That's why we say that the nodes must need to be in sync. Okay?
Could they happen in, could he ask some questions like these in switches, routers, and switches, routers, and
well,
hubs?
all of this has to do with primarily, we're talking about the data link layer. So any device that uses the data link layer, okay, potentially could use slotted aloha. So let's talk about what devices use the data link layer.
It's switches.
So, okay, well, let's start at the very bottom, okay? Do hubs and repeaters use the data link layer?
No.
Okay, so if they don't use the data link layer, they don't care about this. They have no knowledge of it. They don't care about it. How about what devices actually work? Okay, their primary function is in the data link layer. Which devices are those?
They are switches, and they are also routers.
You're correct. Okay. Any other devices that work in the data link layer? What devices are even smarter than routers?
It's like hosts.
Hosts. So that would include any kind of computer system, okay, a printer, a cell phone. These are all devices that work in the data link layer. So they would care about something like this.
Right. And can we do something with switches that has to sort of start Aloha with the example of switches and all the other devices as a similar problem?
Well, what happens is we generally don't get into, and I didn't see them getting into it in the book, about timing and so on, but you need to remember these points here. Okay?
Okay.
All right. Okay, slotted Aloha efficiency. Efficiency is the long run fraction of successful slots, many nodes, all with many frames to send. Okay? So how efficient are we able to move all of these frames from these nodes through the available slots? So how do we figure this out? Suppose n nodes with many frames to send, each transmits in slot with a probability of p. So what he's doing is he's trying to come up with a calculation. He said he was not going to make you go through the calculations, correct?
Give me 1 second. Let me check one more time.
Okay, go ahead.
For 5.2? For 5.2?
Yeah, I don't know if I don't know if it's 5.2. Hold on. We're in 5.3 right now.
Yay! Saying he just says basic mechanisms of static channel partitioning, taking turns, random access, pure and slotted Aloha, CSMA/CD. He doesn't want to know the detailed mechanism of static channel partitioning, taking. I don't think he wants us to know the detail.
Okay, so slotted Aloha. Okay, what technique does that use? I'll tell you right now. It's right here.
Random access protocol.
And here are the examples. Aloha, okay? SMA or CSMA and CSMA-CD and CA. These are all random access protocols. Then you've got channel partitioning. You've got random access and channel partitioning. And if you recall, we've got those three here: channel partitioning, random access, and the one we haven't talked about yet is taking turns.
Right.
Okay?
Right.
So if he says CSMA, Which of these three are you going to go with?
GSMA, it'll be channel partitioning.
Nope. CSMA is random access. How about TDFM?
TDFM?
Or TDM? TDMA. What is TDMA?
Time division multiplexing access.
Okay. Which of the three is this? Channel, random, or taking turns?
It's like channel.
It is. It's channel. See, right here.
Yeah.
Channel partitioning MAC protocols. First example, TDMA. What's the other example that they gave? Do you remember?
It's TDMA, FDMA.
Right. FDMA, frequency division multi-access. These are both channel partitioning protocols. Do you recall what the protocols were for random access?
Random access is, I don't recall one of them.
Okay. Which one?
I don't recall.
Be honest. You don't recall any of them.
I don't recall any.
All right, here they are again. Slotted Aloha, Aloha, CSMA, CSMA CD, and CSMA CA.
Got Aloha, Aloha, CSMA, CS.
Okay. See, here they are, right here. Random access protocols and examples right there.
Got Aloha, Aloha, CSMA, CSMA.
So when he asks you what kind of protocol does Aloha use, you're going to say what?
Random access protocol.
Correct. All right, very good. All right, he doesn't want you to know how to calculate this. That's not necessary.
He doesn't want us to know the details of it.
He doesn't want you to know the details, right? So Aloha uses a very similar technique where it's got time slots and it has frames, okay? Or I'm sorry, it's unslotted, okay? It's simpler and there is no synchronization. And we're not going to get into figuring out the probability.
Yeah.
Or the efficiency.
Yeah, because it's not asking, you have to mind us going into the details.
Right, right. Okay, so here is CSMA. Carrier Sense Multiple Access. Can you tell me what major protocol out there uses CSMA?
It'll be.
You use it in your house. No, you use it in your house.
You use.
What kind of networking do you use in your house?
We use Wi-Fi.
Okay. And what else?
When we also use Wi-Fi and we use
Ethernet?
Ethernet.
Right. So Ethernet is a CSMA, And specifically, Wi-Fi is a CSMA-CA, collision avoidance. And we'll talk about that in a moment, okay? So the key to CSMA is listen before you transmit. If the channel sensed is idle, okay, go ahead and transmit the frame. If the channel is busy, wait until it's quiet again and then transmit. Now here we're trying to calculate the probability of transmitting, okay, without collisions. So let's see. Collisions can still occur. Propagation delay means two nodes may not hear each other's transmission. Okay, spatial layout of nodes, okay. Yeah, I'm not exactly sure what his what he's saying is if two nodes are far enough away from each other, they may not hear the other communicating, and it's very likely that they could collide. So if you have two nodes on opposite ends of the wire, just based on the amount of time it takes to propagate across the wire, they may not hear one another and therefore may not be aware that they're colliding. It's only towards the end of the transmission that they end up colliding. Okay? A collision, the entire packet transmission time is wasted and we have to retransmit. So the role of distance and the propagation delay in determining the collision probability. And that's what they're trying to determine here, the probability of that occurring.
Yeah.
Okay, so we've got CSMA CD, or collision detection. That's what this CD here means. Carrier sensing, deferred or deferral, as in CSMA. In other words, if you sense somebody is transmitting, you wait until your turn comes. Collisions detected within a short period of time. Colliding transmissions are aborted, reducing channel wastage. And when we have a collision detection, easy in wired LANs measured signal lengths compare transmitted and received signals. It's more difficult, however, in a wireless LAN, such as a wireless network. The received signal strength overwhelmed by the local transmission strength. Okay, so just be aware of that. Human analogy, the polite conversationalist. What do they mean by that anyway? The polite conversationalist.
It means that they are easy and gentle and
okay. If someone is having a conversation with other people in the room, for instance, let's say you want to say something and there are other people in the room that are talking, when are you going to attempt to talk?
When the other person finishes.
That's correct. That's what they mean by a polite conversationalist. You are a polite conversationalist because you'll wait until the other person stops talking before you start talking. Okay? So that's what they mean in this analogy.
Can you think of another example like that?
Well, it's just like the classroom. Only in the classroom, classroom is almost like token ring, because in the classroom, the protocol says that if you have something to say, you put your hand up, right? Correct?
Correct.
If you want to say something in class, you first put your hand up, or you take the polite conversationalist, okay, and you wait until somebody else stops speaking. But, many times in class, who's always talking in class?
Professor.
Right. So it's not like you can really wait for the professor to stop. So what we do is we actually put our hand up, say, hey, I've got a question. I've got something to say. And at that point, professor then passes control to you, basically pointing to you or calling your name and saying, Sam, what is your question? At which point you're then able to communicate. Okay? And once you're finished communicating, then you pass control back to the professor, who then either goes on with their lecture or they pass control back to another student who may have another question. Does that make sense?
That makes some sense.
Okay. I can't come up with another analogy for some of this. Yeah, I can't think of anything right off the top of my head.
I couldn't hear you. Can you repeat that?
I can't think of any other examples off the top of my head to describe that protocol. Except that they take turns transmitting. And if two nodes attempt to transmit at the same time, it's a collision, and then the nodes have to retransmit at a later point in time. Okay?
Okay.
So, next we've got taking turns. Taking turns is another access protocol that we have. Okay?
Okay.
And if you recall, we had channel partitioning, we had random access, which we just finished, okay? And then we have taking turn protocols. It is described as best of both worlds. And it's one of the reasons that IBM selected taking turns for their token ring network. You know what the major disadvantage to token ring was?
No.
Technically, it was very good. The problem was that IBM charged too much for it. You know why IBM lost the PC market? IBM used to own the PC market. Okay? Hold on, let me plug my system in. IBM used to own the PC market. Why did they lose it? It wasn't because of the technology, because they always had great technology. Their problem was that their marketing and their pricing structure basically killed them. Companies like Compaq and HP came in and they killed them. Today, HP owns Compaq. Okay? Compaq was a little bit before your time. I don't know if you still remember those computers. All right. Anyway, moving forward. So now we're talking about what is taking turns. Polling. Okay? Now again, think taking turns is just like the classroom, where the master node is the professor. And the master node will invite the slave nodes being the students, to transmit in turn. So as students raise their hand saying, hey, I've got something to transmit, the master node says, okay, Sam, it's your turn. Go ahead and transmit. Ask your question.
And for example, you can also go to the class and say, go ahead, ask your question, for example.
Right, that's correct. So typically, the slaves in this case are not as intelligent, okay? They're often, described as dumb devices. because they don't have a lot of processing capability. Part of the problem that Taking Turns had was polling overhead. It took time to poll the stations and say, do you have a question? Do you have a question? Do you have a question? Going to each student. They also had a single point of failure in that if the master went down, okay, then the whole network went down. So going back to our classroom analogy, if the professor left the room, okay, what happens to the class?
They leave.
The class is done. They can't function any longer without the master being in the room. And then there's the issue of latency, and that simply comes with having to keep polling, okay? So here it is, our Taking Turns and token passing, and we call this token ring. So a control token is passed around to the stations from one node to the next sequentially. A token message is the token. It's nothing more than a digital message. Concerns that they have token overhead, as we said before, latency, and then a single point of failure, namely the master who would generate the token. Okay? And here's a summary of our media access control protocols. Again, this is really important. Write this one down. You want to memorize this this slide.
Memorize
536.
536. Fine.
You want to get that one down hard. Okay?
Okay.
All right.
Do you think he's going to ask similar problems like routers and switches on the test?
With respect to media access control?
Yeah, but with respect to media access control?
No, I think he's going to ask more about switches with media access control than he is routers.
Yeah, what could be put as an example for media? Could we do go
okay.
like?
For instance,
could we go through a written example?
No, wait. No. Okay. A switch, a network switch that you have, okay, in the classroom. Do you know what kind of protocol it uses at the data link layer?
Kind of protocol?
What kind of protocol does a network switch, most network switches that you've worked with, what protocol do they use?
They use DH.
What kind of wiring? No, what kind of wiring is generally used?
It's like wired.
Yeah, but what kind? You know, describe it. Give it a name.
I don't recall. But
Does Ethernet sound familiar?
Ethernet. Yeah.
Okay, and what type of cable does Ethernet use?
802.11.
No. What type of cable, when you make an Ethernet cable, what type of cable is used?
Hold on.
You're not going to be able to do a Google search on this stuff when you're in class, okay?
See. It'd be like a Cat 6.
Okay, all right, fine. But what type of cable is Cat 6? Cat 6 is often used, Cat 5 and Cat 6 is often used in Ethernet networking. But what type of cable is Cat 5 or 6? This is the type of question he's going to be asking you on the test. He may not ask this question because this question goes all the way back to like the first 2 chapters.
Just the first 2 chapters, but 3, 4, and 5 is on there, not.
Right. So the type of cable is UTP. Do you remember what that is?
Unshielded twisted pair.
Okay, unshielded twisted pair. Okay, very good. All right, so that's the type of cable, and the protocol that we often use in our network switches is Ethernet, which uses another protocol called CSMA-CD. However, if you're doing a wireless network, you're going to use 802.11, which is based on CSMA-CA. Okay?
Okay, but how could he ask it as a switch example? How is he going to have an image? Really going to ask it?
No, he's going to say, for a switch, what type of protocols, what data link protocols do we use in a switch?
So he's not going to put like examples on it. He's just going to put. He's just going to ask it in a multiple choice question, not ask. He's not going to put.
Yes. Right. So if he says, what kind of protocol do we use in a switch? He might put 802.11. He might put 802.3. He might put in CSMA-CD or CSMA-CA. What's the proper answer? The answer
CSMA.
is, go ahead.
CSMA-CE. CSMA-CD.
Correct. So, okay. You might also ask the question, the IBM token ring was based on which MAC protocol? Channel partitioning, random access, or token ring, or token passing, or taking turns? And the answer is taking turns.
Taking turns.
All right.
So how many? What are the So the possibility is what is the channel partitioning and the Ethernet, and then what are the questions?
I'm sorry. Say that again. You were breaking up.
What are the questions after that? Is that all the questions he's gonna have after these 3 and these 3?
No, Sam, I don't know what he's going to ask. Okay.
Okay.
Okay. I have no idea. All I'm saying is that whatever's on this page, you should definitely know this.
Okay. I'll try and get this memorized.
All right. Very good.
But I've been trying to go through the definition in the textbook to also memorize too. I've been going through and studying the common definition in the textbook too.
Okay. Very good.
I'm gonna try and get to it. But I also have terms and definition in the book to do. But I'm gonna try and get to 536 and memorize this.
All right. Okay.
I'll try to get through, but I have to go.
Well, Sam, honestly, there's no try here. Okay. We are at the end. We got to get it done. So I can't do it for you. All right.
All right.
All right. So let's talk about link layer addressing. I'm pretty sure he wants you to know this and know it well. So this is 5.4. This is 5.4.
Can we go through this?
Oh yeah, we are definitely going through this. Okay.
I can't do this fast enough, but I'm gonna try and do it. I'm gonna try and do most as much as possible, so I can get ready for the. Yeah.
Yes, please. So to begin with, when we talk about addressing, there are generally two types of addresses that we're interested in. One is called a physical address, and the other is called a logical address. The IP address, specifically IP version 4, is a 32-bit address. Okay? It is also a network layer address, and it's used to get datagrams to the destination IP subnet. Okay?
Right.
The other type of address is a physical address. Some people say it's a LAN address or an Ethernet address. Okay? Some people even call it a burned-in address. Okay?
Okay.
But the MAC address is 48 bits long. And this address is used for getting a frame of information from one interface in a subnetwork to another interface. In other words, to get it from the interface on the router to the interface on a node such as a workstation. What does NIC stand for? What is it short for?
NIC, Network Interface Card.
Network Interface Card. So, if you will, what devices have NICs?
It's like an Ethernet frame. It's like Ethernet frame and routers. Can you hear me?
Yes. Yes, but where do you find NICs? Tell me what type of devices. Routers. Okay, that's one device. Give me other examples.
It'll be like switches.
Switches have them, yeah.
And it can also be hubs.
Hubs can have them too, yes.
Can you repeat that?
Hubs have network interfaces too. What other devices have network interfaces?
It's like Ethernet? An Ethernet cable?
No, give me a device. So we said routers, switches. You forgot about bridges.
Bridges.
And hubs so far. What other devices? In order to plug an Ethernet cable into something, it has to have a NIC. So what devices do we plug Ethernet cables in? What do we got?
We have like a plug, like a UT.
Sam, do you have your laptop?
Yes, laptop.
Okay. I want you to look at the left-hand side of your laptop. You have an Ethernet port over there?
Yes, it says an Ethernet port.
Okay.
Yeah.
An Ethernet port and a NIC are one and the same. Okay?
Could you write this down?
No, you write it down.
Could you write this down a little bit?
No, Sam, the way you memorize things better is if you write them down because it gets into your head. Okay? So you write it down.
Could you? I need something to look at, but I need something written. Ethernet port.
Okay, I'll spell it out for you. Okay? An Ethernet port and a network interface are one and the same. Write that down.
One and the same.
An Ethernet port and a network interface port are one and the same.
Ethernet
port and a network interface port are one and the same.
Network interface port are one and the same.
Right.
Are one and the same. But could you write something down from some other?
Look, Sam, it's right here. The function. Get the frame from one interface to another physically connected interface on the same network. Okay? The NIC, the network interface. Let me ask a question. How often do you go over and you review your notes? Sam?
I go and review my notes like almost every day, but I've been studying the textbook. I can't do it that fast now.
Okay. All right. Your notes are probably the easiest to review because they're in your hand, okay? Generally, when I used to take notes, I would know what the notes would say before I even read it because I remembered writing that particular piece, okay?
I can't take it. No, I can't take it fast enough. I can't take it fast enough.
You can't take the note fast enough?
I can't take it fast enough. I can't take it fast enough.
You can't read it fast enough or take the note fast enough?
I can't take the notes fast enough.
Okay. Okay. All right. Okay.
And I can't read the notes fast enough. I'm trying to get to it fast enough, but I can't study fast enough. I'm going to try and study. I can't study fast enough.
All right. Okay. All right. Okay. You'll notice in this diagram that there are how many nodes on this network?
It'll be 4.
Okay. There are 4 PCs or 4 workstations, and a node is equivalent to a workstation. You'll notice that every node or every workstation also has that green little box. What does that green little box represent?
It represents like the hexadecimal number
No,
and MAC address.
no. What does the green box? It literally tells you on the slide. It
It's
tells you what
adapter.
okay, so and what is another name for the adapter?
It's like the Ethernet. It's like It's like an Ethernet slot.
The other name for the adapter is NIC, Network Interface Card, right?
NIC.
What does NIC? Yeah, what does NIC stand for?
Network Interface Card.
Right. All right.
NIC is equal to adapter.
And
So
go ahead.
Could he like ask a similar problem like this in a scenario type with the file, or could he ask some different type?
No. He may ask, okay, what kind of address is given to a NIC?
What given address is
What kind of address do you find on a NIC?
physical addresses?
Correct. And give me an example of a physical address.
It would be like a MAC address.
Correct. And how big is a MAC address?
48 bits.
Correct. Very good. Now, how many hex digits is the MAC address? We did this on Wednesday, or we did this on, I think, what was it? Tuesday, on Tuesday.
So where
How many digits in a MAC address? If you recall, if you remember, you just said that a MAC address is equal to 48 bits, correct?
yes.
How many bits does it take to represent a hexadecimal digit?
Good. How many represents?
How many bits does it take to represent one hexadecimal digit? You remember our conversation on Tuesday?
So where is that?
Okay, the question again is, how many binary digits or bits does it take to represent one hexadecimal digit? I'll ask another question which will help you to answer the first one. What is the binary equivalent of a hexadecimal F? If I give you a hexadecimal F, tell me what the binary is for that F.
For F, it'll be 4 ones.
Very good. Okay, so right there, the largest hexadecimal value is what?
I'm getting
What's
time
the-
to repeat that.
What's the largest hexadecimal digit that you can have?
Can I go up to F, which is 15 hexadecimal digit?
Okay, so F is the largest hexadecimal digit, correct?
Correct.
And what is the binary equivalent of F?
It's 1111.
4 ones, okay?
Yeah, 4 ones.
So in other words, to represent a single hexadecimal digit takes 4 binary digits.
Right.
Okay, would you agree with that?
Yes.
Now, I want you to take 4, and this is the question we're trying to answer next. How many hexadecimal digits does it take to represent a MAC address? So, if you know that the MAC address is 48 binary bits long, you would take that 48, you would divide it by 4, and it will tell you how many hexadecimal digits you need.
You need 12 hexadecimal digits.
Okay, now, good. Now, I want you to count how many digits are here.
Could you write something down?
No, count how many digits are here.
There's 12.
There are 12, right? And we just
Right.
said that a MAC address is equivalent to either 48 bits or 12 hex digits, okay?
Yeah.
And isn't that what you have there? Therefore, what
Yeah.
you're seeing right here is what? What is this?
These are random hexadecimal digits.
They're random?
They are.
What does this value represent here? What is that?
It's the MAC addresses.
It's the MAC address, right? Which we know to be 48 bits long, but it's also, you can convert it and you can make it 12 hexadecimal digits long.
Right.
Okay?
Right.
Very good. Now, we also know that the MAC address for each node must be unique, correct?
Right.
And that the MAC address is broken into 2 pieces. An
Right.
organizational segment, which is 24 bits long approximately, and then the unique interface, which is another 24.
Yeah.
Okay? All right.
Right. So what could he put as another example? Just the one example?
What could he put as an example?
Yeah.
He would ask the questions I just asked, Sam. For instance, he may say, given this this hexadecimal MAC address, converted into binary. Okay?
Could you also write this down?
You mean write the question down?
Yeah, write the question down.
All right. Sam, I have to be very clear here with you, okay? I can write this question down, but it does not mean that the question is going to be on the test. There are many different ways that he can ask the question. I don't know all the different ways that he's going to ask questions. That's why it's important to understand this in a general way. Okay? You can't memorize the questions. You have to be able to figure this out. It doesn't do any good to write all the questions down because you still won't have them all. I could write 100 questions on this and he could still pick something different. Do you understand where I'm coming from?
Could you repeat the last part? I understood.
Okay. What you're trying to do is you're trying to get me to tell you what all the questions are, okay? That John is potentially going to ask you, okay? And even if I were to give you dozens of example questions, it's possible that he could still ask a different question. Okay?
Okay.
So you need to understand things in a general term. Otherwise, you're not going to be prepared for the test. So, what are the general things that you need to know? That a MAC address consists of 48 bits. And we've already said that. If you look, already said that right here.
Yes.
Okay.
32 bits. And 48 bits.
And I also said that, as you can see right here, the MAC address takes the form of 12 hexadecimal digits broken into groups of 2. Okay?
Right.
All right. And that every adapter is assigned a unique MAC address. And that a NIC, or network interface card, is equivalent to an adapter. Right?
Right.
Okay, good. Those are the types of things that you've got to remember. You're not going to be able to memorize, nor are you going to even be able to get what all the possible questions are going to be. Okay?
I'll try to get to understand it. So they say when I go to the exam and I understand the general idea, then I could answer all these questions. But if I were to understand the question and not the general idea, then it's not going to.
It's not going to help you. It's not going to help. It's actually going to hurt you.
Yeah.
All right. So, MAC addresses are allocated. Allocation is administered by the IEEE, okay, which is a professional organization. Manufacturers buys portions of the MAC address space. So they get assigned addresses that they can use on their systems. Okay?
Right.
If you have a 24-port switch, how many MAC addresses does that thing have?
24-port switch?
Yep. If you have a 24-port switch, this is an example of one of the questions that John could use. Okay? So if you have a 24-port switch, how many MAC addresses do you need?
Hold on. Let me get a calculator.
Okay, you really don't need a calculator. You either know this answer or you don't.
For 24-port switch,
A port, okay, an Ethernet port is like a network interface card, okay?
okay,
If there are 24 ports, there are 24 network interface cards.
good.
So if there are 24 network interface cards, how many MAC addresses are you going to need? The answer to the question is 24 addresses.
24 addresses.
Because remember, okay, every adapter, every NIC gets a MAC address. Or every port. So if you have 24 ports, you need 24 addresses.
Wait.
Okay?
Okay.
All right, very good. All right, so a MAC address is very similar to a Social Security number, and IP addresses are similar to postal address, okay?
Wait.
And I think the reason that they're saying this is that a Social Security number identifies an individual person, where a postal address identifies the location of a home in which many people might live. Okay?
Might identify a location for where they live.
Uh-huh.
Should I write this down? Or should I just listen?
No, it's just another example. Okay?
Okay.
Okay, the MAC address is a flat address space. Okay? And MAC address numbers are portable. Therefore, you can take a LAN card, and here's another term. He's using another term for the same thing. What is another name for a LAN card?
For a LAN card, another term for.
What's another term for a LAN card? What do they mean by a LAN card? Do you know?
It's like NIC.
It's a NIC. It's a NIC. Give me another name for a LAN card.
LAN card. Example is NIC and
Can you think of another name?
I can't think of it. I think it's the. Network adapter. Come on. It would be. I can't think of the name.
You see what I'm writing on here?
I see LAN pod.
LAN card equals NIC equals network adapter equals network interface card. Every NIC has at least one network port. Every port is assigned one MAC address. Let me ask a question. If you install a wireless network card, is there going to be a network port?
If you install a card, there has to be.
Listen. If you install a wireless network card, is there going to be a port? We use ports to connect what?
We use ports to connect Ethernet. We use ports to connect an Ethernet LAN.
Ethernet cables.
Ethernet
Physical cable. Okay. But in a
Right.
wireless network, are we using cables?
No.
Okay. So on a wireless card, on a wireless NIC, do you expect to see a port?
Can you repeat?
Do you expect to see a physical port on that card?
No.
Okay, no, you do not. But you probably will see an antenna. So even though it may not physically have a port, okay, it still is going to get a MAC address. Okay?
Okay.
Okay, good. All right. All right, I'll tell you what, give me 5 minutes, okay? I'll be right back.
Okay.
All right, I'm back.
All right.
Okay. So next we're looking at ARP, or Address Resolution Protocol. Okay, and what's the purpose of ARP?
Could you?
I want you to take a look at this slide that we have on the screen right now. And I want you to tell me, what does ARP do?
The ARP has. So the ARP could have.
The purpose of ARP, okay, is if you have a node's IP address, ARP will get you its MAC address. And it's right here, Sam. That's what they're saying right here. How to determine the MAC address of host B, knowing host B's IP address.
Right. So, could we go through the details a little bit?
Yes, we can. Okay. So, we know that IP addresses are used for getting packets from one network to the next. Okay. But inside a given network, all right, we use MAC addresses. Okay.
Right.
And in this case, one of the things that I want you to look at here is look at these 4 workstations in this LAN, okay? And I want you to look at the addresses, okay?
They have a combination of both MAC addresses and IP addresses.
Okay, look at the IP addresses. And I want you to suggest to me what the subnet mask is for these IP addresses. In other words, if you look at all of the IP addresses here, okay, look for the Go ahead.
It's like a Class C address.
It's a Class C?
Class B.
Oh, B. Yes, it's a Class B address, technically. So a Class B, by default, has a subnet mask of what?
255.255.0.0.
Correct. But what I want you to look at is I want you to notice that, look at the octets 1 through 3. What can you say about the first 3 octets in each one of these IP addresses?
The first three, they are they are 16 bits, but they go up to 16 of 255.
No. Look at octets 1, 2, and 3. What is in the first three octets? Tell me.
Well, the three octets.
Read the IP addresses for me there, Sam. Read me the
It's
first three octets.
That's 7.23. There will be
What?
the IP address is 137.196.7.
Okay, that's the value of the first three octets, correct?
Correct.
Would you agree that the value of the first three octets is the same for all of the IP addresses in this diagram?
Yes.
Okay. So could we make the assumption that the subnet mask is 255.255.255.0?
255.255.0.
No, 255.255.255 3 times .0.
3 times.
Or a /24. Can we say it's a /24?
You can say it's a slash. That can, if it's 192, it would be a /24.
No, you're not getting it. What is the purpose of the subnet mask?
The subnet mask is the purpose. Could we face the question?
Okay. Why do we have the subnet mask? What does it do for us? Does it have any purpose whatsoever?
The subnet mask identifies the CIDR notation.
Well, the subnet mask and the CIDR notation are very closely linked, yes. But what's their purpose? What do they allow us to do? Let me ask another question. Within an IP address, there are 2 pieces. What are they?
They identify the subnet mask and the subnet mask and they have the
Subnet mask is used to pull out from the IP address the network address. And the subnet mask, or CIDR, is simply a different way of writing subnet mask.
right.
All right.
All right. So different way of pulling it out.
Okay. Now, can you tell me what the network ID of this network is?
There'll be 137.196.7.0.
Correct. You got that. Okay. You got that. And how did you figure that out?
Because of the 255, because of that subnet, because of the 24 data notation.
Exactly. Okay. So, we said before, the other day, we said that a network, all of the hosts in a network, or all the nodes in a network, are going to have the same network ID.
The network has the same network ID.
Right. Okay.
Okay, can we go over? Oh, okay. So can we go over the details of this line?
Yeah, we're going to go over the details, but I want to make sure that you understand the fundamentals before we get into the details.
Okay.
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 So every node has, and let me ask a question. We went over this last week. What is the difference between a node and a host?
Between
And
the
I
node
wrote
and
this,
the,
right, and I wrote this down for you last week.
do you have this? I don't see that in the SAM drive.
Yeah, what happens, let's see, file, save as. Yeah, see, this is going into the SAM drive. This is chapter 5.
Yeah, the one from last week I don't see.
Right here, Sam.
Right.
Hosts and routers are nodes.
Host and routers are nodes.
Okay.
So, have you uploaded that from last week? Can you show me where?
Sam, this is in the SAM drive.
This is the SAM drive, but
yeah, this is what John gave us.
Right, but I'm looking. So for last week, I'm trying to find where from last week you sent me that stuff.
All right. Okay. Hold on. Let's do this. Come on. Okay, here's the Google Drive, right? Here's Sam.
Yeah.
We're going to go down to a document called Chapter 5. Chapter 05 PowerPoint. This is what John gave you.
Right, but how about the stuff how about the stuff we went over last week? With stuff that you put down.
What I'm saying is I didn't change this, Sam. All I did was I went over it. I'm not exactly sure what you're asking me for.
Yeah, I'm asking I'm asking, I'm asking for the stuff we went over last session. I'm asking for the stuff we went over last session.
This is it right here. You're looking at it, and you have it. John gave this to us, okay? So I have it and you have it. And I'm pretty sure that we went over it on Saturday. This is what we went over.
You showed me some, I think you showed me some switch examples.
That might have been the other day, okay? But remember that the link layer does talk about switches, okay?
Right. But how about the one from Wednesday? Have you?
Well, that, we already have as well. Hold on one second. Let me pull it up. This right here.
What? What is it called again?
This is called switching network.
Switching network?
Right. And again, it's in the SAM network.
SAM network.
Or, the SAM folder. Here, let me show you. Here's my Google SAM drive, and it's called Switching Network, so it's down here.
Switching.
Maybe it's not down here. SAM drive. No, wait a minute. I just put this in here. Oh, dear. Oh, wait a minute. I pulled this up. We did not go over this on Wednesday.
Yeah, we did not. Yeah.
What we went over on Wednesday, on Saturday, we started with all the way back here at 5.1. Then on Tuesday, okay, we did 5.2. Then tonight, we did 5.2 and part of 5.3. We started 5.3 on Tuesday, and then this is where we're at right now at 5.4.
Okay.
Okay, so you have this document where we talk about the difference between hosts and nodes. And by the way, there's one other node in here, and that conceivably is a switch.
Yeah. And how about the video from Wednesday?
Yeah, hold on. 1 second. Let me open up. There's a document that has all of that. Now it's a lot easier with the videos because I can just download that stuff.
For the Saturday one and the Wednesday one, could you also email me, please?
Email you which?
Like the videos and YouTube.
Oh, I'm gonna send you the links right now. 1 second. Okay, hold on. File. Hold on. Okay, open.
As we went over the basic one of Switch, I think we went over the detailed one.
Okay, 1 second. Shit. Come on. Don't have time for this. Oh dear. Tell you what, Sam, I'll update it later tonight and I'll send it over to you before tomorrow morning.
Okay.
Okay.
Yeah. Now I'm able to view it. I couldn't. I was looking at the base, and I was trying to find it. I was studying the book. I was trying to find time to go over these videos, but I'll try and get to these videos because I don't have work. I don't have work because that was my last day.
Right.
I apologize. I couldn't find time for it, but I'll try and find time to do these videos.
Okay. Well, don't worry about apologizing to me because I'm more concerned about you passing this test. Okay?
Okay.
So we just need to really buckle down the next couple of days because you're taking your test on what, the 24th?
Yes.
24th and the 25th, right? 2 days.
Yeah.
All right.
So
very-
he is going to split it
Okay,
for
good.
the, for the first half and the second half.
All right, great. Okay. Well, it's 9 o'clock and I gotta run, okay?
Okay.
So I will talk to you tomorrow, but you've got to tell me what time, all right?
Yes, I'll text you, but I'll try. I'll let you know next time. I'm not gonna. I won't do this again to you.
Okay.
But I'll just tell you that I'm gonna be a little late.
All right, very good. Very good. Okay?
Yeah, yeah. Last night I was eating my dinner. I apologize about that. And I'll
Okay.
I'll try not
Very
to do this again. But I'll let if I have to. If I needed 50 minutes and I needed the same time, I'll let you know. I'll try to let you know more in advance.
All right, great.
So
Well,
I'll
listen,
try to do that.
have a good night and text me as soon as you know for the time for tomorrow, okay?
For the time till tomorrow,
Yes.
I'm gonna be traveling. I don't know yet. I'll text you tomorrow. I'll text you tomorrow.
Well, we talked about actually working together while you were traveling. So talk to your mom about that, okay?
Yes, I'll talk to my mom.
Okay, great. Have a good night. Bye.
Thank you.